All right, in this example, we have a jet of water that's being deflected by a vane mounted on a cart. So you can see the water coming in here with the velocity v jet relative to the ground and a cross-sectional area A. It hits this cart, and the cart could be traveling at velocity v cart. I think in part A of this, the cart's stationary. Part B, the cart's moving at a constant velocity off to the right. In part C, we're asked to find the acceleration of the cart when it's moving at this instant in time with velocity v cart. So it could be accelerating in part C. So it hits this cart and then is deflected upward by some angle theta. And for parts A and B, we need to find the force in the x direction to hold the cart in place. For part C, where it's accelerating, there are no forces applied. So to determine the force components, this will be a linear momentum problem because you can see the jet is, its linear momentum is changing because it's going horizontally here and then some component of it is vertical here. So we've changed the jet's linear momentum. In order for that to occur, there must be some force acting on this jet, and that force is the force that the cart exerts on the jet. So the jet exerts an equal and opposite force on the cart, and in order to hold the cart stationary, like in part A, we would have to apply some forces to hold it in place. So let's go ahead and apply the linear momentum equation for this problem. So I need to identify a control volume, and the one that I'll choose will cut across the jet and then include the cart. And I chose this control volume because you can clearly see that we have some momentum flux coming in and going out. It's at right angles to the stream, so it'll be easy to do the dot product. It's cutting across where we're applying the forces, and it's really the cart that we're interested in. We want to know whether the force is acting on the cart, what's the acceleration of the cart. So that will be our control volume that we'll use. And then we also need to identify a coordinate system since we're using the linear momentum equation, and we'll use this one on the ground for at least part A of the problem. So this is a fixed coordinate system. It's inertial, so we don't have any acceleration terms in our linear momentum equation. Now, the first thing I'm going to do, though, is I'm going to apply conservation of mass to this control volume because I know that I need to get the velocity of the fluid coming out here. And that'll show up in my linear momentum equation term where I have the linear momentum flux coming out. So I'll apply conservation of mass first. So we'll write out the the conservation of mass equation. It's always a good idea to write out the full equation and then simplify it using our assumptions as well as some of the information we know. For this part A of the problem, it's a steady situation. Nothing is changing with time here, so this first term will be 0 because it's steady. And the second term is the mass flow rate out of the control volume. So we have the mass flow rate out over here. So let's just call that V out for the time being. And let's evaluate what the mass flux or the mass flow rate is there. So we have the density times the relative velocity out. Well, the relative velocity, remember, is the velocity of the fluid minus the velocity of the control surface. Here, the fluid velocity will just be the V out, and we'll break it up into its components. There's a cosine theta I hat plus sine theta j hat, right? So it's cosine theta I hat gives you this part. So there's the V cosine theta. That's the part in the horizontal direction, and of course we have some part in the vertical direction there. That'll be V out sine theta. V out is the magnitude. We're using that coordinate system just as a reminder. And then the control surface velocity here, where it's crossing, is just 0 because the cart's stationary. So it's just 0. So U relative will just be that first term there. So let's write that down. V out cosine theta I hat plus sine theta j hat. And then we do the dot product with the area vector there. So the outward pointing normal vector is in that direction. And that area will be the same area as the the jet itself here, so it's just going to be A going out. And the vector will be the same. The normal vector will have the same components as the velocity out because they're in the same direction. So it'll just be cosine theta I hat plus sine theta j hat. And you'll see that when we do this dot product, this will just be V out, A out, times cosine squared theta plus sine squared theta. It's because we have the cosine dot product with the cosine, sine multiplied by the sine. So that's where we get that from. And then this, of course, is just equal to 1. It's a trig identity. So in the end, for this particular term, we'll just have a rho V out, A out, ultimately, for what's coming out here. Now we need to worry about the mass flow rate coming in over here. So that one will be density times the relative velocity. So it'll be the fluid velocity minus the control surface velocity, but the control surface velocity is 0. The fluid velocity is simply V jet in the I hat direction, because it's just this V jet coming in right here in the positive I hat direction. And then the area vector at this point, let's put the normal unit normal vector. It's pointing upstream, so the area will be A minus I hat. Right? The minus here is because the unit normal vector is pointing in the minus x direction. So that's what we have at the inlet. So when we simplify this down, we'll have rho V out, A out, minus rho V jet A. Sorry, this should not be A out. It should just be A. I think I mentioned that before. So let me fix that here. There we are. That sums together to equal 0. You see the density and the areas cancel out, and so you see that V out is just the same as V jet. So you could have probably figured that out right away just by looking at the problem, that because of conservation of mass, the mass flow rate in coming in here should be the mass flow rate going out there. So the V out had to be V jet. But I just showed it through conservation of mass just to prove that that is the case. Now let's go ahead and apply the linear momentum equation in the x direction. So we'll write out the linear momentum equation in its full form. This first term is the time rate of change of x linear momentum within the control volume. The next term is the net linear momentum, x linear momentum out of the control volume through the control surface. Then we have a body force in the x direction and surface forces in the x direction. There's no acceleration term because our coordinate system is inertial. All right, so the first term is going to be 0 because it's steady. It's not changing with time. Body forces in the x direction will be 0 because all the body forces are in the y direction. We don't have to worry about it in the x direction. Surface forces in the x direction will be a minus fx. So let me go back up to the picture. You can see that surface force right here. We're not worried about any pressure forces because if it's atmospheric pressure all the way out here, it'll also be atmospheric pressure in the jets because they're free jets. So it's atmospheric pressure everywhere here, so it all just cancels one another out. Or if you like to think about it in terms of gauge pressure, it's just 0 gauge pressure everywhere, so you don't have to worry about it. The force in the y direction doesn't show up in our equation because we're only worried about the x direction at the moment. So that's our only surface force. Now we have our linear momentum flux term here. Let's evaluate it first at the inlet. The x velocity of the fluid as it crosses the control surface at the inlet will just be v jet. We're using that coordinate system, and that's in the positive x direction. So that's v jet. And then we just worked out the mass flow rate term moments ago. So at the inlet, it's just the same as this. Notice that this expression here is the mass flow rate. It's the same thing here. So that was, we've already evaluated that term. So I'll just copy it down here. It's minus rho v jet times A. So again, that's this green highlighted mass flow rate term. So that's what's happening at the inlet. Now let's worry about the outlet. So at the outlet, we need the x component of the velocity, and that'll be a v out cosine theta, or since we already know v out is equal to v jet, it'll just be v jet cosine theta coming out. Remember, this is just the x component of the velocity as it crosses the control surface. So that's why we just have the x component, v jet cosine theta. And it's positive because it's in the positive x direction. Now the mass flow rate term we already evaluated. That was given right up here. So we'll just write that out directly. That's rho v jet A. So again, this is the mass flow rate term. That's just this term right here. And v out, recall, again, is just equal to v jet. That's how come that's v jet. The terms that I'm highlighting in yellow here are just the x component of the velocity. You just have to be aware that it's only the x component that we want there. So then we can solve this for the force in the x direction. So if I just change the sign, what we'll end up getting is 1 minus cosine theta there in parentheses. So that's the force required to hold the cart in place under these conditions. Let me go ahead and do the y component while we're at it. Okay, now let's just do the linear momentum equation in the y direction. Okay, so we'll write out the linear momentum equation in the y direction. So this is the time rate of change of y linear momentum within the control volume. Now I'm writing out the rate at which linear momentum leaves the control volume through the control surface. It's the net rate. Here are body forces in the y direction and surface forces in the y direction. So the first term is going to be 0 because it's steady again. The body force in the y direction, so here it's going to be a little different than what we had before. In the x direction it was 0, you can see that here. But in the y direction we have to take all the body forces acting on that control volume. So the body force acting on the control volume will just be the weight, which is mg. So it's the weight of the cart and the little bit of water that's inside here. Now this little bit of water I'm going to assume is negligible compared to the weight of the cart. I really don't have any idea how much water is in here. We're not told the relative size of the area and the depth into the page compared to the mass of the cart and such. So I'm just going to assume that amount of water is negligible. So this term will be approximately equal to minus mg. The minus sign comes because the weight is in the minus y direction. Okay. And then we also have the surface force pushing upward, Fy, so we have to include that in the surface force term. Okay, and then of course there are no pressure forces to worry about as a surface force. We've already discussed that. Now let's evaluate the rate at which linear momentum is leaving or entering the control volume through the control surface. So let's look first at the inlet. Now keep in mind this is the y velocity component of the flow coming in. So when I look over here at the inlet, there is no y component to the velocity. So at the inlet, there is no y linear momentum flux. We don't have to worry about it. The only place we have y linear momentum is at the outlet here. And here, the y component of the velocity is the v out sine theta or v jet sine theta going out. So when we evaluate this, this will be v jet sine theta. That's my y component of the velocity as I cross the control surface. And then we have the mass flow rate term, but we've already evaluated that. That's exactly the same as right here. We evaluated that previously. It's just the same mass flow rate. So we'll write that down. That's rho v jet A going out. That's just the exact same term we've done previously. So I'll highlight it in green. So then in the end, our force in the y direction to hold this steady will be mg plus rho v jet squared a sine theta. All right, so hopefully that all makes sense to you. What we've done is we've just applied the linear momentum equation in the x and y directions, as well as conservation of mass. Probably the toughest part about this part of the problem is just making sure you get the correct component for the x direction, just getting the correct component of the outgoing stream, as well as the one in the y direction, just making sure you get the correct y component of the outgoing stream, and knowing at least for the y component, the incoming stream has no y velocity. Okay, so anyway, that's part A. Now part B of the problem, let's go back up here. What's the horizontal force component if the cart moves to the right at a constant speed v cart? So now the cart's headed to the right at a constant speed. Now to solve this part of the problem, we'll still apply the linear momentum equation again. But before we do that, what I want to do is I'll change my coordinate system. What I'm going to do is I'm going to put my coordinate system on the cart. So I'll put it over here. I'll make this a little XY coordinate system and then put a little stick figure to indicate that I'm riding along on the surface of the cart for this part of the problem. So I'm going to do the linear momentum equation using that coordinate system. Now that one is not inertial. Well, I'm sorry, I take that back. That one is inertial in this particular case. And the reason it is because we're moving at a constant velocity. Let me highlight that because it's important. Constant velocity means that this cart is not accelerating for part B. So that coordinate system, even though it's moving, it's not accelerating. So that still is inertial. So we could either use this coordinate system or this coordinate system. Both are inertial. So let me start with the blue one first. And we're only going to worry about the x direction in this problem. So let's work that out. So we'll write out the linear momentum equation again in the x direction, and I'm using the little x here because that's the coordinate system I'm using. So we'll write it all out. And because my coordinate system is inertial, I don't have to worry about any acceleration terms. Even if I put that in here, let me put it in for a second. Here's the linear momentum equation with the acceleration term in it. This is the acceleration of my coordinate system with respect to an inertial coordinate system. Since my coordinate system is not accelerating, this term would just be 0, so it won't show up. Okay, so now let's evaluate this. We've already said there are no body forces in the x direction. We said the surface force in the x direction was the minus Fx. We said that it was steady. It's still steady. As we're moving along in this frame of reference, it still looks steady. Nothing is changing with time. It all looks exactly the same. So it's still steady. The only thing that will now be different will be this term. Now what we need to do is evaluate what the velocity is in the x direction using our new coordinate system. So let's focus first at the inlet right here. I'm going to erase some of this because it's getting a little messy here. So let me erase a few things. All right. So the velocity coming in here using this coordinate system will look like the speed of the jet. Remember, this is with respect to the ground. Now the cart is moving at a velocity v cart. So the velocity coming in here will look like v jet minus v cart. Okay, so it's always a good idea to look at some extreme cases just to verify. So if the cart was stationary, so if v cart was 0, this would just be v jet, which makes sense. It's coming in at v jet. If the cart was moving as fast as the jet, then it would be vjet minus vjet, it would be 0. That makes sense, because if the cart was moving as fast as the jet, then nothing would come in. So it makes sense. Now, since it's vjet minus vcart coming in here, from conservation of mass, v out will have to be the same. It'll have to be the same velocity. It'll still have to be vjet minus vcart coming out in this direction. And that's just purely from conservation of mass. If you applied conservation of mass to that same control volume, and it's vjet minus vcart coming in, it'll be vjet minus vcart going out. It has to, just by conserving mass for a steady flow situation. All right, so the x component of the velocity coming in here will be vjet minus vcart in the positive x direction. And the x component going out here will be vjet minus vcart cosine theta, because we only want the horizontal component using that coordinate system. So let's write those things down. So at the inlet, it's vjet minus vcart. And then the mass flow rate term will be rho. It'll be vjet minus vcart times the area. And there's a minus sign there. Let me highlight these terms again. This is the mass flow rate term. And this one is our ux term, now using our new coordinate system. The mass flow rate term, you can get this the same way that we found it previously. I'm just not going to work it all out here, but it'll be exactly like this expression that we worked out previously. Remember, this was the inlet when the cart was fixed. The only thing different now would be this would be vjet minus vcart. The area vector is still in the minus I hat direction at this inlet. Okay, so that's why we have the minus here. The minus comes from the area term. So that's at the inlet. Let's do the outlet. The outlet, the x component of the velocity is vjet minus vcart cosine theta. And then the mass flow rate there will be rho vjet minus vcart times the area. So again, I'll highlight the corresponding terms. That's our ux term, and then here is our mass flow rate term coming out. So then when we simplify the equation, what we'll end up getting is fx is equal to rho vjet minus vcart squared, and it'll be times a 1 minus cosine theta. Oh, and there's an area there as well. So that's the result we get when the cart is moving at a constant speed off to the right. So that's the force we would have to apply to keep it moving at that constant speed. And it's worthwhile just to double check that it simplifies back to something we saw previously. If v cart is 0, then it's rho vjet squared a times 1 minus cosine theta, which is precisely what we had previously. So it simplifies back to a result that we already know the answer to, so that's good. Let me rework this problem, this same part B, but now let me use the capital X, Y coordinate system. So I'm going to use, instead of the one fixed to the cart, instead of this one, I'm going to use this one and solve this part B using that one. Now, I recommend that in pretty much all cases when you have a control volume that's moving, it's usually easiest to put the coordinate system on the control volume. So it's usually easiest to use this blue coordinate system. I say usually just to give myself a little wiggle room, but in every case that I've ever come across, it's always better to use that coordinate system fixed to the cart. But maybe I haven't seen some special case where it's easier to use the one on the ground. But it shouldn't matter which one we use. We could either use the one fixed to the cart or the one fixed to the ground. We should still get the same answer because the result shouldn't be dependent on our coordinate system. So let me solve part B using that coordinate system. So when we get to so let's write out our linear momentum equation for that case. I'll just rewrite the whole thing. Okay, we don't have any acceleration term again. It's still an inertial coordinate system, so we don't have to worry about that. Body force in the x direction is going to be 0. Surface force is going to be minus Fx. Okay. Let's now determine this first expression. So this will be the time rate of change of x linear momentum within the control volume. This term will still be 0 because it's steady. Still steady. Even though it's moving, it's actually steady because, let me go back up to the picture. Even if we're standing on the ground and this thing is moving to the right, the mass inside here is not changing with time, right? It's still the same mass. And the velocity of what's happening in here doesn't change with time because it's moving at a constant speed v cart and the jet velocity is constant. So neither the mass or the velocity inside the control volume is changing with time, right? And that's exactly what this term is right down here, is just the mass and the velocity inside the control volume, and it's not changing with time, so it's 0. Okay. Now let's go ahead and evaluate this term. This one gets kind of complicated now since we're using this fixed coordinate system. So the x velocity of the fluid as it comes in here, I'm going to erase some stuff since we're now using a different coordinate system. So the x velocity as the fluid goes here is just going to be v jet. It's just the velocity of the fluid using our coordinate system when it crosses the control surface. So this is just v jet. It's not v jet minus v cart. It's because the velocity of the jet using that coordinate system is just v jet, and that's in the positive x direction. So this one all the way down here is just v jet. Okay, so that's this yellow term that I'm highlighting. Now the mass flow rate term, it's still the same mass flow rate that we had before. It'll still be v jet minus v cart, and there's a minus sign here in an area there. So this is exactly the same as what we had previously because it's just the mass flow rate coming out. If you're not convinced by that, let me just jot it down up here. So remember, the relative velocity is the velocity of the fluid minus the velocity of the control surface. Well, the velocity of fluid in this case is v jet in the i-hat direction, and the velocity of the control surface is v cart because it's moving off to the right-hand side and using our coordinate system. So this is just v jet minus v cart in the i-hat direction. So that's why we still have a v jet minus v cart here. Of course, the area vector is still a in the minus i-hat direction. Whenever you calculate this relative velocity, it doesn't matter what coordinate system you use because the u fluid and the u control surface are whatever coordinate system you use, you're using it for both. And so if the coordinate system shifts in some way, that shift occurs for both of these and it subtracts out. So it doesn't matter what coordinate system you use to find the relative velocity. Okay, so that's the mass flow rate at the inlet. Now let's focus on the outlet. This is where it gets a little bit trickier. So let me go back up to the picture here. I'm going to erase some stuff to give myself some room. Now the velocity going out, if we applied, so now we're using this coordinate system relative to the ground, so you have to keep that in mind. So the velocity out relative to the ground is going to be the following. It's just going to be velocity out relative to the ground will be the velocity out relative to the cart plus the velocity of the cart. This is the kind of the way that I like to think about this. This is a little bit tricky. But the velocity v out relative to the ground is the velocity out relative to the cart, and the reason I did that is because we already worked that part of the problem. And then you just add in the velocity of the cart, and this is cart relative to the ground. Okay, so if I work that out, the velocity out relative to the cart will be v v jet minus v cart. Right, and this will be the cosine. There'll be a cosine theta component in the I hat direction, and a sine theta component. Let me just write it. I'll just do it this way. So this is velocity out relative to the cart, and then we have the velocity of the cart itself that we add in. So the velocity of the cart relative to the ground. So then the velocity out relative to the ground, and then specifically the x component of it will be v jet minus v cart cosine theta, because of this term, and then we add in the v cart. Okay, so I know that looks kind of a little bit messy, but that's what the velocity out here is relative to the ground in the x direction. I'm only putting the x component here because that's all I really need. Okay, so hopefully that makes sense. The way to think about it is we previously found what v out was relative to the cart, is that v jet minus v cart. You take the horizontal component of it, that gives you the cosine theta, and then we have to keep in mind that this whole cart is moving to the right, so we add in that velocity. So that's the term that I have to use down here. So let me write that out. So that's v cart minus v jet. I'm sorry, I've got that backwards. Just double check. V jet minus v cart. That's, try that again. V jet minus v cart cosine theta plus v cart. So that's my yellow term. And then when I do the dot product, this is when I do the mass flow rate term, sorry, this will be exactly the same as what we've worked out previously. It'll just be the density times v jet minus v cart times the area. And the reason for this is just comes from conservation of mass. Since this is the mass flow rate coming in, and we have a steady flow, this has to be the mass flow rate going out. And it's a positive because the area and the velocities are in the same direction. Okay. Well, now if we go ahead and simplify this, on the left-hand side, we're going to have a minus rho v jet minus v cart times the area plus a rho v jet minus v cart squared times cosine theta. Just kind of, I'm multiplying through this times that, plus v cart times v jet minus v cart. Then we have the area. That all is equal to minus fx. Sorry, it's all crammed in there. So this term is this one. This term, if I've multiplied everything out correctly, should be, this first term is just that one multiplied by that. And the second one here is the v cart times that. Okay, so let me continue to simplify. You'll see here this, if I do some rearranging here, okay, so now I have to just do a little bit of algebra. It just gets messy. So that'll be a minus and a plus. Sorry you have to watch all of this, but that's just the way it goes when we do it this method. And let me just double check I've got my sign correct. It's a minus plus plus minus plus, plus minus, okay, and then this is all equal to minus fx. And then we should see some terms should cancel out. So we have a vjet times a vcart here, vjet, vcart there, and then a minus 2 vjet, vcart. So those will all cancel one another out. And then we have a vjet squared here, and plus vjet squared there. So that cancels out. I made some sort of sign mistake. Let me just double check that I've got all this correct. That all looks good. That's good. You know what I'm missing? I'm missing the cosine terms. That's what I'm... Let me try again here. Sorry you have to watch me struggle through the algebra here. Actually, rather than have you watch me go through the algebra, I'm pretty confident that I've got this term correct, and I'm pretty confident I've written that correctly. I know that when we simplify it all down, and again, I'm just going to give you the result because I don't think you want to watch me go through all the algebra. There's really little value added on that. But when you simplify it all down, it'll come to this. I know this because I actually worked it out on a piece of paper, and it's sitting to the side of me here so I can take a look at it. And I'm not going to show you all the algebra in between, but this is what you'll get when you simplify it all down. Now, if you compare that to what we derived earlier, right here, they're the same thing. You actually get the same result regardless of which coordinate system you use. Clearly, using this coordinate system fixed to the ground, it gets very messy. I think this, trying to understand that x component of the velocity is a hard thing visually, or kind of physically to understand. I don't like that. And then there's more algebra involved, as I demonstrated to you just moments ago. I didn't mean to demonstrate that to you on purpose, but nevertheless, you can see it's easier to get tripped up on the algebra on that. You just have to be careful that you carry the terms through properly. But you get the same result. So it doesn't matter which coordinate system we use, either the capital X1 fixed to the ground or the little x1 that's fixed to the control volume. You get the same result. I think it's far easier to use that little x coordinate system. It's much cleaner, and so I highly recommend using that one. All right, so now we've done part B of the problem using two different methods. Let's go to part C. What's the horizontal acceleration of the cart when the cart moves with velocity v cart if no horizontal forces are applied? So we're not going to apply any forces to it in the x direction. Now for this one, again, we could choose a control volume fixed to the ground and get a result that way. I think, as I said just a little bit ago, it's kind of complicated to do it that way, and I don't recommend it. So instead, I'm going to use a coordinate system fixed to the cart again. And then I'll work it out that way. But now that my coordinate system is fixed to the cart and the cart can accelerate, this is now a non-inertial coordinate system. So I'll have an acceleration term in my linear momentum equation. So let's write that out. And we'll solve it. This will go fast, I promise you. So the linear momentum equation in the x direction, write it one more time. Even after this example, you may have this memorized. So now we have to include the acceleration term. So control volume here. Acceleration of my coordinate system, little x, compared to an inertial coordinate system, capital X, like the one fixed to the ground. So let's evaluate the simple terms first. There's no body forces in the x direction, no surface forces in the x direction, because we're not applying any force now. This term will be the acceleration of our coordinate system relative to the ground, but if the cart's moving at velocity v cart and it's accelerating, the acceleration will be dv cart dt. So that's how my coordinate system is accelerating. Its acceleration is exactly the same as the cart's acceleration. And then we multiply it by the rho dV integrated over the control volume. That's just the mass inside the control volume, so I'll just call it M. So that's that term. Let's talk about this term. This one's kind of interesting. This is how the linear momentum inside the control volume changes with time. Now, it's specifically using our little x coordinate system. So relative to the ground, let me go back up to the picture. Relative to the ground, the cart is accelerating now. It's no longer a steady problem. When you stand on the ground, the cart's accelerating, so it's changing with time. But if we're on the control volume here, remember, we're using this blue coordinate system. If we're standing here, the velocity of the cart looks like it's stationary. It looks like the cart velocity is 0. Now, there is some change in the velocity of this fluid stream as it goes through here, but we're neglecting that. We're saying that that contribution is small. The mass in this control volume is dominated by the cart. So this term down here is still 0. It's actually approximately 0 because, again, there's a little bit of fluid that's accelerating in our control volume, but it's approximately 0 because the ux is 0 for most of the mass in the control volume. It's not 0 because it's steady. This is not a steady problem. But it's 0 because the ux is 0. And using our coordinate system that's fixed to the cart, it looks like the cart is stationary as we stand on it. So that's why this is 0. It's because the ux is 0. I think it's very important to, when you set this thing to 0, you state why it's 0. It's not because it's steady in this case, it's because the ux is equal to 0. That's the hardest part about this problem, part C. It's the hardest part. Okay, and let's now evaluate this term. Well, this term will look exactly the same as what we did earlier for part B. The x component of the velocity will be v jet minus v cart, where it's coming in. Mass flow rate there will be minus rho v jet minus v cart times the area. And then going out, the x component of the velocity will still be minus v jet v cart times cosine theta. And the mass flow rate there is density v jet minus v cart times the area. So these terms look precisely the same as what we did earlier for part B, like right up here. Because when we derive this, we use that blue coordinate system, so it looks exactly the same here. All right, so then when we simplify this down, we're going to get a minus rho v jet minus v cart squared times the area plus a rho v jet minus v cart squared times the area times a cosine theta is equal to a minus dv cart dt times the mass. And so the acceleration of the cart will be rho v jet minus v cart squared times the area times, let's see, it'll be cosine, let me just make sure I get this sign correct. It'll be 1 minus the cosine theta, all divided by the mass. So that would then be the acceleration of the cart. Okay, so part C of this problem, what you have to be careful of there is you need to include the acceleration term. And probably the hardest part to conceptually understand is this first term. This is the time rate of change of x linear momentum using our little xyz coordinate system, that blue coordinate system. But just recognize that using that blue coordinate system, the ux looks like it's 0. So that's why this term is 0. Hopefully this part, the linear momentum in and out of the control volume, that part hopefully looks reasonable to you since we did that a couple of times earlier in the problem. Now that we have the acceleration, we could find the velocity as a function of time. The way we would do that is we'd have to solve this differential equation, keeping in mind that v cart is buried inside here, so we'd have to bring the v jet minus v cart to the left-hand side and then be careful with our integral. But we're not going to do that for this part of the problem. The very last thing I'll say is we could also do part C of this problem using the capital X coordinate system. So we don't have to use the little x coordinate system. We could use the capital XY coordinate system and rework this. If we did that, this term would be 0 because that coordinate system doesn't accelerate. This one we'd have to be careful of, just as we showed a little bit ago for part B. But this one would not be 0 if we used the capital XY coordinate system, because with a coordinate system fixed to the ground, the UX changes with time. The mass in the control volume stays constant, but the UX changes with time. So this term would look like a mass times dv cart dt. That's what that would end up looking like. It would look exactly like this term here, but it would just be on the left-hand side of the equation. All right, so we'll end that example there. Hopefully it all makes sense to you. If not, you might want to rewatch this video one more time because it has a lot to it. We dealt with a fixed system, one that's moving at a constant velocity, one that's accelerating, and we also dealt with the y direction for at least part of the problem. So there's a lot in here. Okay, we'll go ahead and end it there.